Hello and welcome to this video. In this video, we are going to write a very basic driver for MCP23017 IC. So basically, this IC is a IO expander, right? So it's used when you have like very few pins on a microcontroller unit and you want to add functionality for more pins. So it falls in a group of chips called IO expanders that are used to provide the port expansion for common, microprocessors, right? So MCP23017 is a very classic. It's a classic IC, 16-bit, as you will see in the datasheet. And I have a couple of them here. And instead of using a library from, external users or external platforms, I want to just write a very basic but functional driver, and I'll show you how to approach that from the datasheet and translate that into code, and how we will get that working. So the IC I have, I'll show you that is this is a expander. So this is a breakout board, but you can see the chip right here. Yeah. So I've connected it to an ESP32, and that is the I2C library, or rather peripheral we are going to use for. Okay, so how I like to approach these is, first I start from the datasheet. We see what's the functionality and capability of this IC and see how we approach it. So I have opened the datasheet for the MCP23017. I'll leave a link in the description for whoever wants to download it, but this is a basic datasheet. So it's a 16-bit IO expander with serial interface. It has this I2C interface. It has SPI interface, but the one that has SPI interface is the MCP23017. Let me change this tool first. Right, so that's that. So you can see this MCP23017 M23S17 has SPI. The one I have has I2C. Okay, so let me change something here. Okay, cool. Right, so this is how it looks like. It has two ports, right, from port 0 to 7, and another port B with pins 0 to 7. So port A and port B, basically each of 8-bit, total 16-bit, plus extra pins that are included. For example, this is VDD, VSS for ground, non-connect, SCK, and SDA for I2C. Then we have a 0, A1, and A2 for selecting the address of the I2C device, and then we have a reset pin that is active low. So basically, for an IO expander, we need to use it for two things. What I intend to use it for is two things. Number one, to control LEDs. You can turn on and off LEDs. Number two is to read, because it's an input output. You can read the pins, right? Whether you connect, for example, a switch or a momentary push button to any of these pins or ports, you should be able to read that pin, the respective pin, right? So this is another diagram showing how it's organized. You can see these two GPIO ports, this one and this other one, the second one. Then I do see extra pins. interrupts. I'm not going to be writing the code for interrupts in this video, maybe in the part 2. And yeah, that's all. So operating voltages between 1.8 and 5.5, I've supplied it with 3.3 volts. And the rest is okay. So the most important thing I need to check is I2C, right? Before that, you can see the pin out description. So these pins for each of the ports are bidirectional, right? They are bidirectional. And I think I've described all of these other ones. That's all. So now when you're writing a device driver, the first important thing you need to check is the device address, number 1. Number 2, you need to check the register addresses, which registers are used for what, and where can you set them, where can you read them, etc. Right? So this datasheet has listed the datasheets, the addresses for all the registers, right? So it has 2 banks, first of all. It has bank 1 and the bank 0. Bank 1 and bank 0. Bank 1 and bank 0. Right. So you can see this is bank 1 and bank 0, each of which has its own addresses. Now, this IC functions in 2 modes. Number 1 is what is called the byte mode, or number 2 is called the sequential mode. Right? So byte mode enables automatic address pointer incrementing. So when you read or write a register, it just automatically, it does not go to the next register. For example, if I'm reading this register, the next read I try to read, it will still be in that same register. Sequential mode basically means it automatically increments the address. So if I read this register, internally they'll automatically increment it, and the next time I try to read, it will read the next register. Right? Okay, so enough of me. Let's type the code, and we'll discover some more things as we write it. So I've created a folder here that is going to contain my code files. So I'm just going to initialize this using platform IO. So right now it's empty. I'm going to say PIO project neat. I'm going to be using the ESP32 dev kit v1. Should be able to initialize that. Right, so we have our code right here. Our templates. So I'm gonna open this with VS Code. Okay, so here it is, the VS Code. All right, I trust the Elva, etc. Okay, so the first thing I want to do is create a file in the SRC. It's called main.cpp. So this file is nothing but this file will be used to increase the font. Yep, shut down this copilot. I think that's fine. So this file is to test the MCP23017 driver. So obviously, if you're documenting it, you wanna follow the right procedures. Normally, I use Doxygen, so it has these tags that you're supposed to use. Brief, for example, brief describes what this file is for, and then the file name is the name of the file. I'll show you how this is useful when we are generating the documentation for this driver, for this library, right? So the next thing you do is the alva is that's me doing. All right, you can add dates, you can add licenses, etc., but that does not matter in this case. So I'm gonna include Arduino because we are using the Arduino framework under platform IO. And then the next important thing is the wire.h library. This wire.h is basically a library that controls the I2C protocol for the Arduino devices. For example, the ESP. You know, you are using that specific framework. So they'll save us from writing the hardware I2C. You don't want to write I2C. You want to use I2C to write a driver that uses the I2C, right? So that's why we include that wire. Then two major functions we need is the void setup and the void loop. Right. So we will be using the serial monitor. So serial.begin baud rate, which is 115,200 for ESP. Define baud rate as this is 115,200. Cool. Right. So tuning the current is too big. Okay. Cool. Right. So the next thing is we wanna open the include file and create two files. Create the MCP23017.h file, data file, and then we wanna write the CPP. Let's put the CPP in the SRC folder. So MCP23017.ctt. Right. So obviously in the CTP file we include our header file like that. Then we include, okay, that's fine. We leave it at that. And then here in the header file, we'll say if we check header file inclusion for the preprocessing part, if MCP 3017 H, if defined, right? If it's not defined, include it. 017H. Basically, this prevents double inclusion. CPP, you can use pragma once, basically, but I prefer this C method definition of, avoiding multiple inclusions. Okay, so the first thing we include here is the Arduino library. And then we include the wire to enable us to use the APIs for I2C, right? So another thing, the way I like to approach it is that I start from the application side. So how am I going to use this driver, right? So what I finally, or rather at the end I want to do is initialize, for example, an LED connected to a specific pin. I want to say something like expander dot pin mode. Say pin mode, a pin number which is 0, for example. Or we can say define the LED 1 or LED 0, B0. And then we say LED 0. Pin mode, I want it to be an output, right? So that it lights up, drives the LED. So expander.digital, right, LED 0, maybe high, light it, right? So this is how I intend to use it. Now, because you can have multiple expanders. There are two ways to connect them. So you can connect them through you can chain them through I2C and use different addresses, or you can have different objects as the expanders. So I also want to be able to initialize this expand as a class object or as an object. So I want to say something like this, expander, like that, right? Maybe the address. So this is how I'm going to use it. This is how I'm going to use it. So let me say expander address, right? Which means I need to define expander address, which we will resolve later. Something. Expander address will be something, some hexadecimal value. So in the setup, I want to say expander dot init. So mind you, all of these functions are not implemented, right? So this is giving me a template of what I need to implement in the driver. So I'm going to split this editor, split editor, right? So I'm just gonna push this there, and we'll have a class, right? I don't want that. MCP23017 now class, and then we want to have two things: public, right, and private. So I put private first. Private. Okay. So yesterday the constructor is public, obviously. So I'm gonna say MCP23017. They should not have a bracket here. Now the constructor expects. Remember, when you are constructing, we need to pass the address. So we pass a uint8 t address. Something else I need to include is std int to give me access to like the defined size variables like uint8, uint16, etc. Okay. It should be not defined. Okay, so that's that. The next thing I need to implement is init function. So should return a bool or a uint8 init, right? Init, and then I need to have a void pin mode. So pin mode will take two things: a pin, which is a uint8 t pin, and uint8 t the level or the mode. Let's call it the mode. This is uint5th, right? The level and the mode. So let me this. Yep, let's monitor how I'm recording. Right, cool. So the next thing we need to implement is digital write. So we need to void digital write. What are we writing to? Right, we need to write to a pin. So pin, and then the level, high or low, right? To check whether it's high or low. So uint8t level, I'll call it level. All right. So we saw that this MCP23017 has a reset pin, so we can reset. Just write the pin low. Something else, we need to be able to read given pin. So digital read a pin uint8t pin and uint8t. No, that's enough. Just to read a single pin. Now, there are other utility functions that are very useful. For example, when we need to write a register, read a register, etc. So when we need to write a register, we need to pass register. We need to pass the address of a register, and these addresses are 8-bit. So and do that register address. Okay, just address, and then when you are reading, we expect to return a byte. So we can say read register, and of course we pass the address of the register we need to read. Okay, right. So I'll open the implementation file, include the mcp.h, and implement these functions. Right. So the first thing you implement is the class, obviously. No, is the class functions, right? one thing I need in the private is the address of the device. So device, we call it device address. Okay. So when you construct this driver, I want to take this address and set it as the address of this specific instance. So here I will say MCP23017. Constructor is just like that. Then we take unit HD. We are taking the address. Then I want to say this device address is the address that has been passed. So we have access to the address of this instance, right? So let me just document it as I go. So brief, this is a constructor. Okay, so let me just make it look better. Okay, then the next thing we want to implement is the initialization. So you need brief this function initializes the device via I2C. Okay, so init is it8. So I'll say you in 8t MCP23017 init init, right? So what you should do is should check is the device available in the I2C bus, right? Is it available in the I2C bus? So it means this device is a slave for ESP. ESP is a master. That's how I2C operates, master-slave configuration. So it means in the I2C, in the ESP32, we need to initialize ESP32 as a master. And the way you do that, you say wire dot begin, you pass it the hardware pins that are connected to SDA and SCL. Basically, it's 21 and 22. So 21 is for SDA, 22 is for SCL, right? So this will set ESP slave, in master mode, right? Set ESP in master mode. Now, the next thing in the init, let me put this on here. Let me put it right here. In the init, we need to say wire dot begin transmission to a device address, this device address. Okay. So what happens is that ESP will search for this device address on its bus. If it's found, it will return a 0. A 0 is for success, right? So if so here we can say, let's see, we can say begin transmission and end transmission. So we begin transmission to this device address, and then we say wire dot transmission through sends a stop bit, right? So we don't expect any other byte to be sent on the wire bus, and it returns an integer variable that is 0 if it was successful, it found that device address or not. So if it returns a 0, we can easily check the inverse of that and return a 1 if it was found, else return a 0, right? Okay. You realize that this can be simplified. We can just say return the opposite of status, right? Return that, so I can get rid of that, shortening my code. Right, so the other thing we need to do now is we don't have this address. I like to write functions as I test them. So you realize that we don't have the address of this device. So how do we get that address? Right? How do we get that address? So we go to the data sheet. Where's the data sheet? Data sheet should be somewhere. Yeah. Okay. So the data sheet shows that, let's look for the address. Address should be somewhere. Yep. This is SPI addressing. There's no, okay, this is I2C addressing registers. This one, right? So you can see there is a fixed digit here, 0100. You can see that. And then you see the address that can be set by the hardware pins. So if we tie all of these pins to ground, that means we'll have, let me open the calculator to show you that, we'll have 0101 00, and then the rest of them will be 0. Now you can see now this is 0, this is hex is 40. But the problem is, not the problem, but the caveat is that I2C uses, most of it uses 7-bit addressing. 7-bit addressing. So it means that the last bit is always reserved as a control bit, can be read or write. Okay, so that means that this one's not supposed to be here, it's supposed to be here because it's 7-bit addressing, right? So this is this pin, or this 0 right here, is the 6th bit. So 0, 1, 2, 3, 4, 5, 6. 6th bit is right there. So this one should be placed at that position, which gives you an address of 0x20. So this is what we need to look for in the I2C bus, right? So let's try that and see whether we find the device on the bus, right? So here we say 0x20, and MCP23017 is undefined there because they have not included it here. Include MCP23017 H, right? So that's that. So what do you want to do? We want to check, before you even initialize these things, we want to check what is the return value on the init function. Okay, so yeah, if it is initialized, okay, we want to see your print MCP23017 found on bus, right? Else you want to say it's not found, depending on the status. Right, MCP23 is not found. Not found. Okay, so let's compile these and see whether it even runs or compiles in the first place. I need to put a delay here for like 10 milliseconds to give the serial time to start. So the way you run this code in platform IO is just keep PIO run. That will compile it. I will compile. Meanwhile, as it compiles, I want to show you something else on the datasheet. So the next thing we are going to do is define these addresses so that we know which address is connected to what. And then, yeah, we move on from there. But first we need to find the device on the bus so that we know at least we are, doing something. Right. Configuration registers, etc. So I'm just skimming through the datasheet to see what else I might need. All right, so I think we are done compiling. So I'm going to connect my ESP and connect my device. See whether it's found or not. Let's go. Yep. So it's just basic connection I2C to I2C SD821, I2C SEL22, VCC and ground to 3.3 and ground respectively. When we run, I'll upload this code to the ESP and wait and see. So because we have already compiled it, should be faster this time around. And then I'm going to open my serial monitor tool and reset the I2C. Cool. So if you look clearly, you can see we have found the device on the bus, right? MCP23017 found on bus. Yeah, that's a good sign. So next we can go on to the next functions. I'll just minimize this, and write. So let's write a function for the pin mode. Let's try to set pin mode high. Now, one thing that is missing is the addresses. Address descriptions. No, register addresses. Description. Cool. So it means that I need to convert all of these registers to the code. Here they are, all of this. So if you look at the code cleanly, I need to use this device when the bank is 0. So these are the addresses I'll be using, this column right here, not this one. This is the column I'll be using, right? This column. So I listed them before so that I don't waste time like writing them. They are just straightforward. You just write dir a, give it an hexadecimal value. So I'll just copy that and paste it so that it doesn't really take a lot of time. I'll put it right here. Okay. Bank 0 register address description. Okay. So that's that. These are all the addresses from the datasheet, straight from the datasheet. And we are going to use that to set the pin mode. So right here we say void MCP23017 pin mode. We expect to have a pin we're going to write high to bin, and the mode. So you enter T, or the mode can be input or output. Okay. So let me just explain the logic of how this pin mode works. So this device has an IO. Okay, this device first has 2 ports, port A and port B, right? Port A starts at 0 and ends at 7. Port B starts at 0 and ends at 7, but the addresses are different. So when you pass a pin, we need to know in which port is that pin connected to, right? So the pin can be connected to port A or to port B. So we need to resolve which port, which means if I pass something like 12, I want it to pass, if I pass like 12, and the first port is between 0 and 7, it means 12 is in the second port, right? So let's say I have, how do I show that? Let's say I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is a 16-bit, right? This is 16-bit. But port A is ending at that point, port B is ending at this point. So if I pass 12, it means this is mapping to 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. But 7. Yeah. 1, 2, 3. Okay, this should be 0. So it means if I pass maybe pin 9, this would be the pin 1 of the next. Pin 1 of the next port, right? So to resolve this is very easy. You use a mod operator basically to know how does it loop back, right? How does it loop back, or what is the reminder after we divide it by 8? So to show that, I will just run Python, going to do the calculation. So for example, if we pass pin 7, or let's say we pass pin 2, we mod it by 8. That is pin 2 of port A. We pass 3, mod it by 8. That's pin 3 of port A. If we pass 12, mod it by 8, it is 4, right? So it's pin 4 of port B. Okay, that's the logic that we have here. So I'm going to delete this and implement that to resolve which port we are using. So I'm going to create an integer 8 t register. I'll call it reg is equal to the foundation. We want to check. I'll use a ternary operator here and say because we are setting the mode of the pin, we want to use the direction register, right? No, we want to use a GPIO register from the datasheet. Let me check again. Let me check. So we have a direction register released to set the direction of the pin. That's input or output. Then we have this GPIO B in GPIO A right here. But let's look at the description for that. IOCON GPPU. Let's look at the port register right here. So the GPIO register reflects the value of the port. Reading from this register reads the port, writing to the register modifies the output latch register. Right, cool. So I want to check if pin is less than 8, then the mode is the register is GPIO A, right? And then if it's more than 8, the register is GPIO B, like that, right? Okay, so which port? Now the next thing we want to do is check the direction register, right? The direction register. So we want to do this. We want to check what is the pin value. So I'll create a UE80 pin. Let me call it T is equal to. So we'll say pin mod 8. Right? Pin mod 8. T is equal to pin mod 8. Yeah. So, because we want to set the pin mode, we are not interested in the GPIO A registers. We want to check the IOD registers. This is IOD B and IOD A, like that. Okay. So we saw which port, then we read the register to see the values that are there. Then we modify, we set the value for that pin. So this means that, let me just comment it better. Set the value for the pin. So if it's output, you want it to be an output, we set it to 0. Rather, we clear that pin. If we want it to be an input, we set it to 1. Set. Like that. Right? And then from there, we just write the register. Or we send that value to the directional register. Right? Cool. So we want to read the existing or the current value from the register first. So we use I2C obviously. So to do that, we say wire dot begin transmission. This device address. Then you say wire dot. The next thing we send is the address that we want to read from. So you wanna read this address right there. We wanna check what is in that address. Then we end transmission. Let transmission. Now, head transmission expects 2 things, false or true, right? So false means that once it's done, like writing this uint8 value to the register, it does not close the channel, right? It does not send the stock bit. It waits for another byte to be sent on the bus. The next byte we send is a request, right? We request from the device how many bytes we want to request or to read. So this device under address, and then we want to read just 1 byte, right? And then we read down the device right here. So this sequence is simple. So requesting does not actually read the device. It just puts the value of the register in the I2C buffer. Then the read is the one that transfers from the buffer to our value here. So right here, you want to put the register value and read it that way, right? So this is the value of the current IO direction register. So we want to take that pin, check the pin, right? It's 0 or high if the mode is input or output, right? So we check here if mode is input is a 1. So we set this reg value to, so we set bits using OR operator. We OR it with mask, which means we shift 1 into the pin that we want that way, right? Else, if mode is output, what do? We clear that bit. So we clear bits with an AND operator with using 2's complements basically. So with the mask, we shift 1 into the pin, and yep, that should work, right? Now next thing we do, we update. Now we update is the IO dir register. So meaning we write using I2C to that register. So obviously we begin transmission here. Begin transmission. Device address is this. Device address, right? Next thing, we always write the register we want to write to. So wire.write register. So register address is right there. It is this one, the one that we resolved after checking if the pin is less than 8 or not. So that's a register address. And then we want to say wire dot write the value of that register. So I to see basically the first byte it will write is the register address, the second byte it will write is the value. Okay, and that is actually clearly shown in the, I think in the data sheet. Let me look for it. Yeah, here it is. The first thing is the address of the register. Second thing is the register. No, the first thing is opcode, which is the device address. Second thing is the register address. The third byte can be data, can be any number of data that you need to write. Okay, so that's the sequence. That's why we have two writes right here. And for that, we end transmission. So we end transmission and tell it, do not expect any other byte from us by passing in a true into the I2C bus, right? So this basically means we know restart. Now restart. Yep. So yeah, that's the pin mode. So again, if I go through it, first of all, the user can pass any pin between 0 and 15. We check. If it's less than 8, it belongs to port A. If it's more than 8, it belongs to port B. We define a variable that will hold the value that we read from the register. We just want to sample what is existing in that register first. Then this function helps us know if the pin is in port B, what number is it? Between 0 and 7 as a mod operator, right? Now, the next thing we do is read the register. So we begin transmission by sending the device address. We write the register address. Then we end the transmission. Then the next thing that the slave device will send will be the value of the register. All right. And then we pass that to our register value variable. Now, next thing is if the user can pass pin mode as input or output. So if it's output, we set the IO direction register to 0, which means we clear it. You clear bits using OR operator. So OR shift with, you OR with our mask, which is a 1 shifted to the pin number. Otherwise, if the mode is output, we set, this is setting, not clearing. This is set. So we set bit with OR. Then we clear them. We use complements using AND operator. Clear the bit. And then from there, final thing is we update the IO direction register by writing the modified value of that pin to the IO dir register. This function right here should be able to set the pin mode. So I don't want this to be too long. Part 2 of this we'll write the next function, which is the digital write, and maybe blink an LED of 2 and see how it goes. So let me know if you have any question. The link to this code is in the description, and I will see you in the next one.